7 earthquakes above magnitude 5 struck the same island in the Philippines in under 3 weeks. The strongest was a magnitude 6.2, shallow enough to collapse buildings and send an entire province into emergency shelters overnight. All of them ruptured on or near the same structure. A fault that runs the entire length of the second largest island in the archipelago, cuts through cities holding millions of people, and has produced some of the deadliest earthquakes in Southeast Asian history. The Philippine Fault Zone has been breaking in pieces since late June, and seismologists watching the sequence say the pattern does not match aftershock decay. By the end of this, you will understand what is actually moving under that island, why the geometry of this sequence worries the people tracking it, and the one measurement that determines whether this stays moderate or escalates into something the country has not seen since 1990. If this is the kind of content that helps you understand what is actually happening beneath the ground, subscribe now. We cover seismic and volcanic activity worldwide, every week, with the data and the context that most coverage leaves out. Hit subscribe so you do not miss what comes next. On the 28th of June this year, at approximately 2:17 in the afternoon local time, a magnitude 5.4 earthquake ruptured beneath the province of Leyte in the eastern Visayas region of the Philippines. The depth was 10 kilometers. The epicenter sat about 14 kilometers southwest of the town of Calubian on the northern end of Leyte Island. The Philippine Institute of Volcanology and Seismology, PHIVOLCS, located it within minutes and issued a public advisory. Shaking was reported across 6 provinces. No fatalities, minor structural damage, and a population of roughly 200,000 within 30 kilometers of the epicenter. 4 days later, a magnitude 5.1 struck 22 kilometers to the south-southeast at the same depth. Then on July 5th, a magnitude 5.7 arrived between the 2 previous epicenters. July 9th brought a magnitude 5.3. July 12th, a 5. July 14th, the largest of the sequence so far, a magnitude 6.2, directly beneath the municipality of Villaba at a depth of just 8 kilometers. And on July 16th, a 5.4 again, this time 15 kilometers further south along the same structural trend. 7 events above magnitude 5 inches 19 days, and more than 340 smaller earthquakes recorded alongside them. The entire sequence sits on or immediately adjacent to the northern segment of the Philippine Fault Zone, one of the most seismically dangerous structures in the Western Pacific. If you judge this by the magnitudes alone, you could talk yourself into calling it moderate. A 6.2 is a serious earthquake, but it is not a catastrophe on a national scale. The Philippines experiences earthquakes routinely. The country sits in the most seismically active belt on Earth, the Pacific Ring of Fire, and magnitude 5 events are common enough that they rarely make international news. That framing is badly incomplete, and here is why. The Philippine Fault Zone is not an ordinary fault. It is a left lateral strike-slip structure running approximately 1,200 kilometers from Lingayen Gulf in the north to the Davao Gulf in the south. It cuts the entire archipelago nearly in half. Crucially, it does not behave as one connected rupture surface. It is segmented, with each segment capable of independent failure, and the boundaries between segments are where the complexity lives. The fault moves at roughly 20 to 35 millimeters per year, depending on the segment, which makes it one of the fastest-moving crustal faults in the world. For comparison, the San Andreas Fault in California moves at about 25 millimeters per year along its fastest section. The Philippine Fault carries comparable rates through terrain that holds roughly 10 times the population density. That slip rate needs a moment, because it sets up everything that follows. 20 to 35 millimeters per year means that locked segments of this fault accumulate strain rapidly. A segment that has been quiet for 100 years has stored 2 to 3.5 meters of potential slip. That is enough to produce a magnitude 7 or larger. A segment quiet for 200 years could store enough for a magnitude 7.5. And on the Leyte segment specifically, the paleoseismic evidence and the historical record both point to recurrence intervals between major ruptures of roughly 100 to 200 years. The last great earthquake on the Leyte segment struck on August 2nd, 1918. That event is estimated at magnitude 7.6. It killed more than 120 people and generated a local tsunami in the Leyte Gulf. 107 years have passed since then. That arithmetic does not predict anything. Recurrence intervals are averages, not schedules. A fault that breaks every 150 years on average might break at 80 years or at 250 years, and nobody can tell which it will be. But when a segment with that much elapsed time starts producing clusters of moderate earthquakes, seismologists pay attention. Not because a cluster guarantees a larger event, but because it reveals that the fault is active, accumulating stress, and shedding small failures in a pattern that demands interpretation. The word that matters in this sequence is not magnitude, it is migration. And that brings us to the observation that makes this worth more than a routine advisory. Look at the epicenters plotted in time order. The first event on June 28th was at the northern tip of the active zone. The second, 4 days later, was 22 kilometers south-southeast. The third was between them but slightly further south. Each subsequent event has added length to the active zone, stepping down the fault like a slow-motion zipper. The July 14th, magnitude 6.2, the largest event, landed at the southern end of the zone, 40 kilometers from where the sequence started, and the July 16th event extended it a few more kilometers still. Over 19 days, the actively rupturing segment grew from a point to a 50 kilometers band. That is migration. Migration along a strike-slip fault is not inherently alarming. It is documented behavior. But it is also the signature of progressive stress transfer, where each rupture loads the adjacent section of the fault and nudges it closer to failure. When that process continues in one direction, it is called cascade, and cascade is how moderate sequences become large ones. The 1990 Luzon earthquake, magnitude 7, ruptured approximately 120 kilometers of the Philippine Fault zone in a single event. The question that matters right now is whether this 50 kilometers migration stabilizes or continues extending. PFALX is explicit about this uncertainty. Their public bulletins note that the earthquakes are associated with movement along the Philippine Fault zone and that aftershocks and further moderate events are expected. They have not issued a forecast for a larger event, and the science does not allow one. What they have done is extend the damage assessment to all municipalities within the affected zone and instructed local authorities to inspect all public buildings within 30 kilometers of the fault trace. That assessment is finding damage. The magnitude 6.2 on July 14th produced peak intensities of 7 on the PHI-VOLCS earthquake intensity scale in Villaba and surrounding barangays. At that intensity, heavy furniture moves, walls crack, chimneys break, and poorly constructed masonry can collapse. 14 residential structures were classified as totally damaged. 47 more sustained partial damage. 3 schools were shut for inspection. A section of the national highway developed cracks wide enough to require lane closure. The provincial government activated evacuation centers, and approximately 4,200 people spent the night of July 14th outside their homes. The depth of that event is the key to the damage, 8 kilometers. At that depth, a magnitude 6.2 delivers significantly more surface violence than a deeper event of the same size. The energy does not spread over as large a volume before reaching the surface. It arrives concentrated, sharp, and loud. People in Villaba describe the shaking as a sudden explosion followed by violent lateral motion lasting about 15 seconds. That description matches the mechanism perfectly. A shallow strike-slip rupture produces horizontal acceleration, which is exactly what knocks masonry walls sideways off their foundations. Now, here's what the data cannot yet tell us. Is this sequence a swarm, a foreshock, main shock, aftershock sequence, or something else entirely? The distinction is not academic. It determines what comes next. In a normal main shock aftershock sequence, the magnitude 6.2 is the main event. Everything before it was foreshock activity, everything after it is aftershock decay, and the sequence should taper off over the coming weeks following a well-understood statistical model. If that is what this is, then the 6.2 was the ceiling, and the hazard declines from here. In a swarm, there is no clear hierarchy. The events are driven by an external process, usually fluid movement or slow slip, and the sequence can produce multiple events of similar size over an extended period. Swarms do not follow clean decay curves, and they can re-intensify after apparent quiet. If this is a swarm, predicting the ceiling is not possible from the data alone, and there is a third possibility that the Philippine seismological community is monitoring carefully. Foreshock sequences to large earthquakes are rare but real, and they look, in the early days, exactly like what we are seeing now. Migration along a fault trend, moderate magnitude stepping progressively along the structure, and a failure to decay on schedule. The 1990 Luzon earthquake had foreshock activity in the days before the main rupture. The 2019 Cotabato earthquake sequence, which produced 3 events above magnitude 6 inches, a span of 2 weeks on the same fault system, demonstrated that the Philippine Fault zone is capable of sequential failure across multiple segments in rapid succession. The honest answer is that nobody can distinguish these 3 scenarios in real time with any instrument. The classification is only available after the sequence ends. If it ends now, it was a main shock aftershock sequence. If it produces another large event, the 6.2 becomes a foreshock. And if it keeps going without clear hierarchy for weeks, it was a swarm. The probabilities favor the first interpretation. Following any given earthquake, the base rate for a larger event within the next week is roughly 5 to 6%. That means 19 times out of 20, the 6.2 is the biggest this sequence will produce. The reason to keep watching is not that it probably will escalate, it is that the 5% case cannot be ruled out and cannot be detected in advance. There is a published body of work on this specific segment that sharpens the concern. Research led by scientists at PIVOX and collaborating institutions, published over the past decade, has mapped the stress state along the Philippine Fault Zone using GPS geodesy and seismicity catalogs. The findings are direct. The Leyte segment of the fault is accumulating elastic strain at a rate consistent with its geological slip rate. The last major strain release was in 1918. The estimated slip deficit on this segment, meaning the amount of movement the fault owes based on its loading rate, is between 2 and 3.5 meters. That is the strain budget for a magnitude 7 to 7.6 earthquake. This does not mean a magnitude 7 is coming tomorrow. Slip deficit is a loading measure, not a timer. Some faults accumulate centuries of deficit and release it in small events spread over decades. Others store it quietly and release it all at once. The Leyte segment has done both in its documented history. The 1897 event was moderate. The 1918 event was catastrophic. The fault's behavior is episodic and irregular, which is precisely what makes it dangerous, because irregular faults give no schedule to plan around. The comparison that matters most here is not to California or Japan. It is to the fault's own recent history on a different segment. In October of 2019, a magnitude 6.6 struck the Cotabato segment of the Philippine Fault Zone on Mindanao. It was preceded by a 6.3 2 weeks earlier and followed by a 6.5 2 weeks later. 3 events above magnitude 6 inches 1 month, all on the same fault system, each one stepping along the structure. That sequence killed at least 23 people and displaced more than 200,000. It was not predicted, and each successive event was larger than what aftershock statistics would have suggested from the event before it. The mechanism in Cotabato was sequential segment failure. One segment ruptured, transferred stress to the next lock section, and that section then failed on its own schedule. The gaps between the events, roughly 2 weeks each, were not random. They represented the time required for the stress perturbation to push the adjacent segment past its failure threshold. The geometry of the current Leyte sequence shows the same spatial pattern at a smaller scale. Migration direction is consistent, stepping is regular, and the inter-event times are shortening rather than lengthening. That last detail, the acceleration, is what keeps this on the active watch list. There is a complicating factor in the Philippine Fault Zone that does not exist in most other strike-slip systems worldwide. The fault runs through an island arc undergoing active subduction on both sides. The Philippine Sea Plate is subducting beneath the eastern margin at the Philippine Trench, and the South China Sea is subducting beneath the western margin at the Manila Trench. This means the stress field on the Philippine Fault is not controlled solely by the fault itself. It is being squeezed, pulled, and rotated by subduction processes that operate on different timescales and produce their own earthquakes independently. In the Leyte region specifically, the Philippine Trench lies approximately 60 kilometers to the east. Large subduction earthquakes on the trench interface can change the stress state on the Philippine Fault, both statically and dynamically. A 1924 magnitude 8.1 on the Philippine Trench produced measurable stress changes on the Leyte segment of the fault. The system is coupled. Movements on one structure affect the other. And the Philippine Trench produced a magnitude 7.2 inches 2023 offshore Mindanao, close enough to the southern segments of the Philippine Fault to have perturbed the regional stress field. None of this constitutes a prediction. It constitutes context. The Leyte segment is loaded. It is moving. The recent subduction activity offshore has likely added incremental stress. And the current sequence is migrating in a direction and at a rate that resembles known precursory patterns on this same fault system. Every one of those sentences is defensible from the published science. None of them individually requires a large earthquake to follow. Together, they describe a system that is doing something, and the something has not finished yet. Let us address the claim that has been circulating on Philippine social media since the magnitude 6.2 on July 14th. The claim is that PHIVOLCS knows a magnitude 7 or larger is coming and is withholding the information to prevent panic. The data does not support this interpretation, and the reasoning is specific. PHIVOLCS publishes its earthquake bulletin in real time, accessible to anyone with internet access. The focal mechanisms, depths, magnitudes, and locations are all public record. The agency's official statements have been measured and factual, noting that further moderate events are possible and that the sequence is associated with the Philippine Fault Zone. They have not issued a major earthquake warning because no science on Earth can issue such a warning. Earthquake prediction, in the sense of specifying a time, magnitude, and location in advance, does not exist as a capability anywhere in the world. What exists is probabilistic forecasting, and the probabilities right now say that this sequence is more likely to decay than escalate, while acknowledging openly that escalation cannot be ruled out. The second claim worth addressing is that this sequence is connected to the recent volcanic unrest at Tal and Canlaon volcanoes. It is not, and the distances involved make the physics clear. Taal is approximately 600 kilometers from the current seismic activity. Canlaon is roughly 150 kilometers away on a different island. While both volcanic systems are active in producing their own earthquake sequences, the stress transfer between a magnitude 6.2 shallow crustal earthquake and a volcanic system 150 kilometers away is effectively zero. The strain fields do not interact at those distances for events of this size. These are independent processes happening on the same tectonically active archipelago, which produces earthquakes and volcanic activity constantly across its entire extent. 3 active things happening in the Philippines simultaneously is not a signal. It is a Tuesday. The building stock in the affected region deserves frank discussion because it is the factor that converts earthquake magnitude into human consequence. Leyte province has a population of approximately 1.7 million people. Much of the housing, particularly in rural barangays, is constructed of concrete hollow blocks with minimal reinforcement, wooden frames with galvanized iron roofing, or mixed materials that do not meet modern seismic standards. The National Building Code was updated in 2015 to include more stringent seismic provisions, but enforcement outside major urban centers is inconsistent, and the vast majority of existing structures predate the update. A magnitude 6.2 at 8 kilometers depth produced 14 totally destroyed buildings and forced 4,200 people from their homes. Scale that to a magnitude 7 at similar depth, and the physics alone tells you the outcome. Magnitude is logarithmic. A magnitude 7 releases approximately 31 times the energy of a 6.2. It ruptures a fault area roughly 10 times larger. The duration of strong shaking extends from 15 seconds to potentially 45 seconds or more, and the area experiencing damaging intensities expands from a radius of about 30 kilometers to potentially 80 kilometers or more. Within that expanded radius on the Leyte segment live approximately 800,000 people. The disaster preparedness infrastructure in the Visayas region has improved substantially since Typhoon Haiyan in 2013. But seismic preparedness specifically, meaning retrofitting, early warning capability, and evacuation protocol for earthquake rather than typhoon, has received less investment and less public attention. The timeline of what has happened since the magnitude 6.2 matters for what comes next. In the 48 hours following the July 14th event, PHIVOLCS recorded 67 aftershocks, with the largest being a magnitude 4.8. That aftershock rate is within the expected range for a 6.2 main shock. The July 16th magnitude 5.4 is slightly larger than standard aftershock statistics would predict at that time interval, but not dramatically so. What matters more than the size is the location. It was further south than any previous event in the sequence. The active zone grew again. If the sequence were behaving as a simple main shock aftershock, the aftershocks should cluster around the 6.2 epicenter and remain within the rupture area of the main event. Instead, they continued to extend the zone. That is the observation that keeps this from being routine. As of the most recent PHIVOLCS bulletin available, seismic activity on the Leyte segment continues at an elevated rate. Events between magnitude 2 and 4 are occurring daily. The rate has not returned to background levels. In a textbook aftershock sequence following a magnitude 6.2, the rate should have declined to near background by now. It is not. That does not mean escalation is certain. It means the process is not finished. Here is what to actually watch, and it is 3 specific things. First, watch the southern end of the active zone. If the next event above magnitude 5 occurs further south than the July 16th epicenter, the migration is continuing, and the fault is progressively failing along strike. Each southward step adds length to the stressed zone and brings the sequence closer to the next major segment boundary, which lies approximately 40 kilometers south of the current terminus. That boundary is where the fault changes orientation slightly, and segment boundaries are where ruptures either stop or jump. If this sequence reaches that boundary while still producing moderate events, the probability assessment changes significantly. Second, watch the depth distribution. The current sequence is shallow, between 5 and 12 kilometers. If events start occurring at 15 to 20 kilometers depth, that indicates the rupture is penetrating into the lower part of the seismogenic zone, where larger fault areas become available for failure. Deeper events in this context would suggest that the process driving the sequence is accessing more of the fault surface, which is a necessary precondition for a significantly larger rupture. Third, and most importantly, watch the aftershock decay rate. The modified Omori law gives a quantitative prediction for how aftershock rates should decline with time following a main shock. If the observed rate remains above the predicted rate for more than 2 weeks after the July 14th event, the sequence is not behaving as a simple aftershock process. Either something else is driving continued activity, or the largest event has not yet occurred. That 2-week threshold is not arbitrary. It is approximately the time scale over which the 2019 Cotabato sequence produced its successive large events. The GPS stations operated by PIVOX along the Philippine Fault Zone in Leyte provide one additional data stream that may become diagnostic. If the fault is undergoing slow slip, meaning aseismic movement of the kind documented on subduction zones and some strike-slip faults, the GPS stations should record a transient displacement that exceeds what the cumulative seismic moment of the earthquakes can account for. Early reports suggest that displacement has been detected, but the processing required to separate tectonic signal from noise in the Philippine GPS network, which operates in a tropical environment with significant atmospheric moisture, takes time. If confirmed, slow slip beneath the seismogenic zone would change the interpretation entirely. It would mean the fault is being loaded from below by a process that produces no earthquakes of its own but delivers stress to the brittle upper crust, where it is released as the events we are recording. That mechanism has been documented on the North Anatolian Fault in Turkey and on the Alpine Fault in New Zealand, and in both cases it preceded significant earthquakes by weeks to months. The historical parallel that hangs over all of this is 1990. The Luzon earthquake of July 16, 1990, magnitude 7, ruptured 120 kilometers of the Philippine Fault Zone on the island of Luzon. It killed more than 1,600 people, destroyed entire towns, and triggered massive landslides that buried communities. That earthquake arrived without a clear foreshock sequence. But the fault segment it ruptured had been identified in retrospect as having shown elevated microseismicity in the months prior. The problem is the same one that exists everywhere in seismology. The warning signs are only identifiable as warning signs after the event they supposedly warned about has already happened. The Leyte segment is not the Luzon segment. Different island, different geometry, different loading history, but it is the same fault system, the same tectonic regime, and the same type of structure. And it is currently producing a sequence that has lasted 3 weeks, migrated 50 kilometers, produced a magnitude 6.2, and shows no sign of having finished. That combination warrants monitoring. It does not warrant panic, and the difference between the two is measured in the specific observables laid out above. Watch the migration direction. Watch the depth. Watch the decay rate. If all three stabilize over the next 10 days, this sequence will settle into the catalog as a notable but non-escalatory cluster. If any of the three continues to deviate from expectation, the conversation about this fault changes. The Philippine Fault Zone has been reminding Leyte of its presence for 19 days. It has not yet done anything that exceeds the historical range of behavior on this segment, but it has also not stopped, and nothing about a fault carrying 107 years of accumulated strain suggests that it has forgotten how to produce the kind of earthquake its geology demands. The monitoring continues. The data is public, and when this fault moves again, you will hear about it here.